So here's something kind of wonderful to think about as you're settling in tonight. Right now, wherever you are, you're surrounded by vibrations. The hum of an appliance somewhere in the background, maybe the faint buzz of electricity in the walls, the way your own voice would resonate in your chest if you spoke out loud. Vibrations are everywhere. They're one of the most basic things in the universe. A guitar string trembles and makes a note. A drumhead shakes and makes a sound. Your phone screen refreshes millions of times because tiny crystals are oscillating inside it. Vibrations are so fundamental, so ordinary, that we barely think about them. And yet, there's this idea, this wild, ambitious, occasionally maddening idea, that vibrations aren't just something that happens in the universe. They might be what the universe actually is. Down at the very bottom of everything, beneath the atoms, beneath the quarks, beneath anything we've ever been able to see or measure directly, there might be tiny, unimaginably small loops of vibrating energy. And the way they vibrate, the pattern, the frequency, the mode, that's what determines whether something is an electron or a photon or a quark or gravity itself. Everything you've ever touched, every star you've ever seen, every thought flickering through your mind right now, all of it, maybe, is music. Tiny, impossibly small music, playing on strings so small that if an atom were the size of our entire solar system, one of these strings would be about the size of a tree. That's string theory, or at least, that's the poetic version. The real version is messier and stranger and more fascinating, and it has a history that's genuinely one of the weirdest stories in all of physics. Because string theory wasn't invented by someone sitting down and saying, "I bet the universe is made of strings." It was discovered almost by accident, while people were trying to solve a completely different problem. And then it refused to go away. For over 50 years now, some of the smartest people who have ever lived have been pulled into its orbit, seduced by its mathematical beauty, frustrated by its resistance to experimental proof, and unable to fully let it go. Tonight, we're going to walk through all of it. Slowly. Gently. No rush. If you drift off somewhere along the way, that's perfectly fine. That's kind of the point. But if you stay with me, I think you'll find that string theory, for all its reputation as this impossibly abstract thing that only geniuses can understand, is actually built on ideas that are surprisingly intuitive once someone lays them out for you in the right order. So let's start at the beginning. Not the beginning of string theory itself, we'll get there, but the beginning of the problem it was trying to solve. Let's go back to the 1960s, the mid-1960s specifically. This is a really interesting time in physics. On one hand, things are going spectacularly well. Quantum mechanics, which had been developed in the 1920s and 1930s, has proven to be the most successful theory in the history of science. Its predictions match experiments to an absurd number of decimal places. Quantum electrodynamics, QED they call it, can predict the magnetic moment of an electron to something like 10 decimal places of accuracy. That's like predicting the distance from New York to Los Angeles and being accurate to within the width of a human hair. It's unbelievable. So the quantum world is looking pretty good. And on the other side, you've got general relativity, Einstein's masterpiece from 1915, which describes gravity as the curvature of space-time, and that's working beautifully too. It predicts the bending of light around massive objects, the precise orbit of Mercury, the expansion of the universe. Two incredible theories, two towering achievements of human thought. But here's the thing. They don't talk to each other. Quantum mechanics governs the very small, atoms, particles, forces at subatomic scales. General relativity governs the very large. Planets, stars, galaxies, the overall shape of the cosmos. And within their own domains, they're both essentially perfect. But the moment you try to combine them, the moment you try to write down a quantum theory of gravity, everything falls apart. The math produces infinities, not useful infinities that you can cleverly work around, the way Feynman and Schwinger and Tominaga figured out how to do with QED in the late 1940s. No, these are ugly, uncontrollable infinities. Nonsense answers. The theories are fundamentally incompatible, like two pieces of software written in completely different programming languages, trying to run on the same machine. Now, in the 1960s, this problem is known, but it's not what's keeping most physicists up at night. What's keeping them up at night is something more immediate, more chaotic, and honestly kind of embarrassing. It's the strong nuclear force. Let me set the scene. By the mid-20th century, physicists know about four fundamental forces. There's gravity, which we all know. There's electromagnetism, which covers light, electricity, magnetism, chemistry, basically everything you interact with on a daily basis. There's the weak nuclear force, which is involved in certain kinds of radioactive decay. And then there's the strong nuclear force, which is the force that holds the nucleus of an atom together. Think about what that force has to do. Inside the nucleus of every atom, you've got protons packed together. Protons are positively charged, and positive charges repel each other. That's basic electromagnetism. So, something has to be holding those protons together against their electromagnetic desire to fly apart. That something is the strong force, and it is, as the name suggests, strong. It's about 100 times stronger than electromagnetism at nuclear distances. It's the most powerful force in nature. But in the 1960s, nobody understands it. Not really. And the reason nobody understands it is that when you smash particles together at high energies, which is what physicists do, that's their thing. They build bigger and bigger accelerators and smash things together and see what comes out. When you do this with strongly interacting particles, what comes out is a zoo, an absolute zoo of new particles, dozens of them, then hundreds. Particles called pions and kaons and RO mesons and sigma baryons and omega particles and on and on and on. Every time they cranked up the energy, more particles appeared. It was like opening a closet and having an avalanche of stuff fall on you. And nobody could figure out the pattern. With electromagnetism, you had a beautiful theory, QED, where there's basically one force-carrying particle, the photon, and everything is clean and elegant. With the strong force, it was chaos. Which of these particles were fundamental? Were any of them fundamental? How were they related to each other? Nobody knew. This is the environment into which string theory is accidentally born. And the person who takes the first step, without knowing he's taking it, is a young Italian physicist named Gabriele Veneziano. Veneziano is working at CERN in Geneva in 1968. He's 26 years old, and he's not trying to revolutionize physics. He's trying to do something much more modest. He's trying to find a mathematical formula that describes how strongly interacting particles scatter off each other. When two pions collide, what's the probability that they bounce off at this angle versus that angle? That's the kind of question he's working on. And here's what's remarkable. He's flipping through a mathematics textbook one day. And this is one of those moments in the history of science that almost feels too good to be true. But it really happened. And he comes across something called the Euler beta function. It's a function that the Swiss mathematician Leonhard Euler had written down way back in the 1700s. for purely mathematical reasons that had nothing to do with physics. And Veneziano realizes that this function, this 200-year-old piece of pure mathematics, has exactly the right properties to describe the scattering of strongly interacting particles. It matches the data. It has the right symmetries. It's beautiful. He publishes his result in 1968, and it causes a stir. Other physicists start playing with it, extending it, building on it. But there's a mystery at the heart of it. The formula works, but nobody knows why it works. It's like finding a key that opens a lock, but you have no idea who made the key or what's behind the door. And then, in 1970, 3 physicists working independently, Yoichiro Nambu in Chicago, Holger Beck Nielsen in Copenhagen, and Leonard Susskind in New York, all figure out the same thing at roughly the same time. They realize that Veneziano's formula, this mysterious mathematical expression that so perfectly describes particle scattering, can be derived from a physical model. And the model is this. What if the particles aren't points? What if they're tiny, one-dimensional strings? Think about that for a second. Up until this moment, every particle in physics has been modeled as a point, a zero-dimensional dot with no size, no shape, no internal structure. An electron is a point, a quark is a point, a photon is a point. That's how quantum field theory works. But Nambu, Nielsen, and Susskind are saying, what if that's wrong? What if, at some incredibly tiny scale, particles are actually little vibrating filaments of energy? And the beauty of it is that a string can vibrate in different ways. Just like a guitar string can play different notes depending on how it's plucked, a fundamental string could vibrate in different modes, and each mode would look like a different particle. One vibration pattern gives you a particle with this mass and this charge. Another pattern gives you a particle with different properties. Suddenly, the zoo of particles isn't a zoo at all. It's an orchestra. Different instruments, different notes, but all coming from the same kind of string. Now, Leonard Susskind, and this is a great little story. Susskind is working at Yeshiva University in New York when he figures this out. He's a fascinating character. He grew up in the South Bronx, the son of a plumber. He actually worked as a plumber himself before going into physics. He's got this wonderful, no-nonsense New York personality, and he's brilliant. And when he realizes that Veneziano's formula describes vibrating strings, he gets incredibly excited. He writes up his paper and submits it to a major physics journal, and they reject it. The referees don't buy it. They don't see why anyone should take this seriously. Susskind is frustrated, but he keeps pushing. He eventually gets it published elsewhere, and slowly, the idea starts to gain traction. But let me be clear about something. At this point, in 1970, this is not a theory of everything. This is not a theory of quantum gravity. This is not even called string theory yet. It's called the dual resonance model, or sometimes the string model of hadrons, and it's specifically and only about the strong nuclear force. It's an attempt to explain all those mesons and baryons that were coming out of particle accelerators. That's it. Nobody is thinking about gravity. Nobody is thinking about extra dimensions. Nobody is thinking about the fundamental nature of reality. They're just trying to understand why pions scatter the way they do. And for a few years, it looks promising. The model makes some interesting predictions. It attracts some talented young physicists. But there are problems. Some of the predictions don't quite match experiment. The model seems to require 26 dimensions of space, which is, a lot. That's a hard sell. And it predicts the existence of a massless particle with spin 2 that nobody has ever observed in the context of the strong force. That last problem, the massless spin 2 particle, is going to turn out to be incredibly important. But we'll come back to that, because right around this time, in the early 1970s, a completely different approach to the strong force is gaining momentum. It's called quantum chromodynamics, or QCD, and it's based on the idea that the strongly interacting particles, the protons, the neutrons, all those mesons and baryons, are made of quarks held together by force-carrying particles called gluons. And QCD works. It works really, really well. It explains the particle zoo beautifully. It makes precise predictions that match experiment. By the mid-1970s, QCD has essentially won the battle for the strong force, which means the original motivation for string theory has evaporated. The problem it was invented to solve has been solved by someone else. Most physicists move on. The number of people working on string theory drops to a handful. It looks like a dead end. A beautiful mathematical curiosity that turned out to be the wrong answer to the question it was trying to address. And this is where the story could have ended. This is where string theory could have become a footnote in the history of physics. A clever idea that didn't pan out. But something strange happens. A few stubborn, brilliant people keep working on it. And they start to notice something extraordinary about that embarrassing massless spin 2 particle, the one that had no place in a theory of the strong force. Because there is one place in physics where a massless spin 2 particle belongs. There's exactly one thing it could be. It could be the graviton, the hypothetical quantum of gravity, the particle that, if gravity is a quantum force like the other 3 forces, must exist, but that no one has ever detected and no other theory has been able to consistently describe. And if the strings are producing gravitons, then string theory isn't a theory of the strong force at all. It's something much bigger. It's a theory of gravity, a quantum theory of gravity. The very thing that physicists had been chasing since Einstein, the great unification that nobody could make work. And here it was, hiding inside a model that was originally built to describe protons smashing into each other. Think about how strange that is. You set out to understand one thing, you fail at it, and in failing you accidentally stumble onto something far more profound. It's one of the most remarkable plot twists in the history of physics. And the people who recognize this, they deserve real credit, because it was not an obvious move. The key paper comes from Joel Scherk and John Schwartz in 1974. Scherk is a young French physicist, brilliant and intense, working at the École Normale Supérieure in Paris. Schwartz is at Caltech. And together they make the argument explicitly. Stop thinking of string theory as a theory of hadrons. Start thinking of it as a theory that includes gravity. The massless spin 2 particle isn't a bug. It's the whole point. Now, here's what they had to do to make this work, and it's a detail that matters. In the original hadronic string theory, the strings were imagined to be about the size of a proton, roughly a femtometer, 10 to the minus 15 meters. That's small by everyday standards, but actually pretty large by particle physics standards. It's a scale you can probe with accelerators. But if the strings are supposed to be producing gravitons, if they're supposed to be the fundamental fabric of gravity, then the relevant energy scale is completely different. It's the Planck scale. And the Planck length is about 10 to the minus 35 meters. That's 20 orders of magnitude smaller than a proton, 20 powers of 10. It's almost incomprehensibly tiny. If a proton were the size of a tree, the Planck length would be smaller than the proton originally was. You'd need an accelerator the size of the galaxy to directly probe strings at that scale. So Scherk and Schwartz are saying, These strings are real, but they're unimaginably small, and the theory naturally contains gravity because it naturally produces this massless spin-2 particle that behaves exactly the way a graviton should. And the physics community's response is, basically, silence. Almost nobody cares. It's 1974. QCD is the exciting thing. The standard model of particle physics is coming together beautifully. Electromagnetism and the weak force have just been unified by Glashow, Weinberg, and Salam. QCD is handling the strong force, and everything is working. Why would you pay attention to this weird theory that requires 26 dimensions and talks about gravity at energy scales you could never hope to reach experimentally? It seems like science fiction. Shirk and Schwartz are essentially shouting into the void. And this is where the human story gets poignant. Joel Shirk struggles. He has health problems, personal difficulties. He continues to work on string theory and supergravity through the late 70s, but the lack of recognition takes a toll. He dies in 1980, at just 33 years old. He doesn't live to see string theory's revival. He doesn't live to see the ideas he championed become the hottest topic in theoretical physics. There's something deeply sad about that, about someone who sees the right answer before everyone else and doesn't get to witness the world catching up. Schwartz, meanwhile, keeps going. He's at Caltech, and he just doesn't stop. Year after year through the late 70s and early 80s, when almost nobody else in the world is working on string theory, John Schwartz keeps plugging away. He later described this period as lonely. Imagine that. You believe you're working on something genuinely important, maybe the most important thing in theoretical physics, and your colleagues are polite about it, but clearly think you're wasting your time. That takes a particular kind of stubbornness. Or maybe it's faith. Or maybe it's just that the mathematics is so beautiful you can't put it down. But let's back up for a second, because there's a crucial development we need to talk about that happens in the early 1970s, right around the same time that string theory is losing its original purpose, and it involves one of the most important ideas in modern physics, supersymmetry. Here's the setup. In the world of quantum particles, there are two fundamental types. There are bosons, which are the force-carrying particles, photons, gluons, the particles that transmit interactions. And there are fermions, which are the matter particles, electrons, quarks, neutrinos, the stuff that makes up you and me and everything we can touch. The difference between them comes down to a quantum property called spin. Bosons have integer spin, 0, 1, 2. Fermions have half-integer spin, 1/2, 3/2, and this distinction is deep. It's not just a labeling convention. Bosons and fermions behave fundamentally differently. Bosons are gregarious. You can pile as many as you want into the same quantum state. That's why lasers work, all those photons marching in lockstep. Fermions are loners. No two identical fermions can occupy the same state. That's the Pauli exclusion principle, and it's the reason atoms have structure, the reason chemistry exists, the reason you don't fall through your chair. So bosons and fermions seem like completely different animals, but in the early 1970s, several physicists, Pierre Ramond, André Neveu, John Schwartz again, and others, discover that you can build a version of string theory that includes both. The original bosonic string theory, the 26-dimensional one, only produced bosons. It couldn't account for fermions at all, which is a pretty serious limitation if you want to describe the real world, since, matter exists. But this new version, which gets called superstring theory, includes a mathematical symmetry that relates bosons and fermions to each other. That symmetry is supersymmetry. And here's what's really elegant about it. Supersymmetry says that for every boson, there should be a corresponding fermion, and vice versa. They come in pairs, like dance partners. The photon would have a partner called the photino. The electron would have a partner called the selectron. The quark would have the squark. I know, the naming convention is a little goofy. You just stick an S in front for the bosonic partner of a fermion, or add eno for the fermionic partner of a boson. But the underlying idea is profound. It's saying there's a hidden symmetry in nature that connects the two most fundamental categories of particles. Now, nobody has ever detected any of these supersymmetric partner particles. The Large Hadron Collider has looked hard and hasn't found them. So supersymmetry, if it exists in nature, must be broken at the energy scales we can currently probe, meaning the partner particles are much heavier than their counterparts, and we haven't had enough energy to produce them yet. Or maybe supersymmetry isn't realized in nature at all, at least not in the simple way people first imagined. That's an open question, and it's an important one. But for string theory, supersymmetry does something magical. It fixes problems. Remember how the original bosonic string theory required 26 dimensions? The superstring theory, the one with supersymmetry, requires only 10. That's still a lot more than the 3 spatial dimensions plus time that we experience, but it's a significant improvement. Going from 26 to 10 feels like progress. And there's another fix that's even more important. The bosonic string theory had this particle in it called the tachyon, a particle with imaginary mass that would travel faster than light. That's a sign that the theory is unstable, that the vacuum state you're expanding around isn't really stable. It's like trying to balance a ball on top of a hill. Any tiny perturbation and the whole thing rolls away. The tachyon is a deep sickness in the bosonic theory. But in the superstring theory, the tachyon goes away. Supersymmetry kills it. The theory is stable. So now, by the mid-1970s, you have this situation. There's a version of string theory, superstring theory, that lives in 10 dimensions, naturally includes gravity via the graviton, incorporates both bosons and fermions through supersymmetry, and is free of the tachyon instability. On paper, it has a lot going for it, but almost nobody is paying attention. The theory still has unresolved issues. There are actually several different versions of superstring theory floating around, and it's not clear how they relate to each other, or which one, if any, describes reality. And the extra dimensions. What do you do with 6 extra spatial dimensions that nobody has ever seen? This is where an old idea gets dusted off and put to new use. Back in the 1920s, a physicist named Theodore Kaluza, and later the mathematician Oscar Klein, had proposed something wild to Einstein. They said, what if there's actually a 5th dimension of space beyond the 3 we see? And what if this extra dimension is curled up so small that we can't detect it? Kaluza showed that if you write down Einstein's equations of general relativity in 5 dimensions instead of 4, something remarkable happens. The extra components of the gravitational field in that 5th dimension look exactly like electromagnetism. You get Maxwell's equations for free, just from the geometry of this extra dimension. Einstein was intrigued, but ultimately the idea didn't go anywhere at the time because quantum mechanics was just getting started and there were bigger fish to fry. But for string theorists, the Kaluza-Klein idea is exactly what they need. If the theory requires 10 dimensions, but we only see 4, then maybe the other 6 are compactified, curled up into a tiny geometric shape at every point in space, so small that we can't detect them directly. And here's where it gets really interesting. The shape of those curled-up dimensions isn't arbitrary. The specific geometry of the compact space determines what particles and forces appear in the 4 dimensions we can see. Different shapes give you different physics. So the question of why does the universe have the particles and forces it has becomes, in string theory, the question of what shape are the extra dimensions. That's a beautiful idea. It's saying that the laws of physics we observe might be a consequence of geometry. Not just the law of gravity, which Einstein already showed was geometry, but all the laws, electromagnetism, the nuclear forces, the masses of particles, everything. It all comes from the shape of these hidden dimensions. And the particular class of shapes that works best for preserving supersymmetry in 4 dimensions has a name that sounds like it belongs in a fantasy novel. They're called Calabi-Yau manifolds, named after Eugenio Calabi, who conjectured their existence, and Xing-Tung Yau, who proved they were mathematically real. These are 6-dimensional shapes of extraordinary complexity and beauty. If you've ever seen pictures of them, well, you can't really picture a 6-dimensional object, but mathematicians can create projections and cross-sections, and they look like intricate crystalline structures folded in on themselves in ways that are hard to describe verbally. Just imagine the most complex origami you've ever seen, and then imagine it has 6 dimensions and is smaller than a plank length, and you're in the right neighborhood. But here's the thing about Calabi-Yau manifolds. There are a lot of them. Not just a few candidate shapes for the extra dimensions. There are tens of thousands of known families, and within each family, there can be continuous parameters you can adjust. The number of distinct possibilities has been estimated at something like 10 to the 500. That's a 1 followed by 500 zeros. And each different Calabi-Yau shape gives you a different version of physics in 4 dimensions. Different particles, different forces, different constants. So string theory doesn't just predict one unique universe. It seems to predict an astronomically vast landscape of possible universes. And we'll come back to that because it becomes one of the most controversial aspects of the whole enterprise. But we're getting ahead of ourselves because in the early 1980s, most of this is still in the future. The immediate problem is more basic. String theory has these beautiful features, but it also has potential fatal flaws. And the most dangerous one involves something called anomalies. In quantum field theory, an anomaly is when a symmetry that exists in the classical version of a theory gets destroyed by quantum effects. And certain anomalies are deadly. They render a theory mathematically inconsistent, full of infinities that can't be removed, predictions that give nonsensical answers. The standard model of particle physics is carefully constructed to be anomaly-free. All the particles and their charges are arranged just so, in a way that all the dangerous anomalies cancel out. It's one of the most remarkable features of the standard model, actually. It looks like it was assembled by someone who knew exactly what they were doing. So the question hanging over superstring theory in the early 1980s is, does it have anomalies? Because if it does, then all the beautiful features, the graviton, the supersymmetry, the elegant mathematics, none of it matters. The theory would be dead on arrival. And this is where John Schwartz finally gets a partner who shares his obsession. His name is Michael Green, a British physicist, and together they set out to answer this question definitively. They work on it for years, and what they find, in the summer of 1984, in a calculation that Schwartz later described as the most exciting moment of his scientific life, is that superstring theory is anomaly-free. But not just in some generic way. It's anomaly-free only for very specific choices of the gauge group. And the calculation is breathtaking. Green and Schwartz sit down and work through the anomaly cancellation conditions for type 1 superstring theory, and what comes out is that the anomalies cancel, every single one of them, but only if the gauge group is SO32. That's a very specific mathematical structure, not any old symmetry group, not something you get to choose freely. The theory itself is telling you what the symmetry has to be, and the way the cancellation works is almost miraculous. You have these different contributions to the anomaly, from gravity, from the gauge fields, from mixed terms where gravity and gauge fields interact, and they all have to cancel simultaneously. It's like having 5 different equations that all need to equal 0 at the same time, and you only have one free parameter to adjust. It shouldn't work. But it does. Green and Schwartz announced their result at a workshop in Aspen, Colorado, in the summer of 1984. And the effect on the physics community is electric. Edward Witten, who is arguably the most influential theoretical physicist of his generation, hears about it and immediately recognizes its significance. Within weeks, he and 3 collaborators, Philip Candelas, Gary Horowitz, and Andrew Strominger, show that there's actually a second gauge group that also cancels all anomalies, E8 times E8. And this one is even more exciting, because E8 times E8 is large enough and has the right structure to potentially contain within it the symmetry groups of the standard model. You could, at least in principle, imagine breaking E8 times, E8 down through a series of steps until you arrive at something that looks like the SU 3 times SU 2 times U, one gauge symmetry of the real world, the symmetry that governs quarks, leptons, and all the forces we actually observe. This is the moment that everything changes. This is what physicists call the first superstring revolution, and it happens fast. Within months, hundreds of physicists who had been working on other things, grand unified theories, supersymmetric field theories, quantum gravity approaches, pivot to string theory. The number of papers on string theory explodes. Graduate students who had been warned away from the subject suddenly find that every faculty member wants to talk about strings. It's one of the most dramatic shifts in the history of theoretical physics, and it all traces back to that anomaly cancellation calculation. Now, let's slow down for a moment and appreciate what just happened from a human perspective. John Schwartz had been working on string theory for over a decade at this point. More than 10 years of being largely ignored, of giving talks to half-empty rooms, of watching his collaborator Joel Shirk struggle with depression and die young. Schwartz kept going. He kept believing that the mathematics was too beautiful, too consistent, too rich to be wrong. And in the summer of 1984, the world finally caught up. Think about what that must have felt like. A decade of intellectual isolation, and then suddenly you're at the center of the biggest revolution in theoretical physics since the development of the standard model. Schwartz has said in interviews that those months were surreal, that he went from being a somewhat marginal figure to being one of the most sought-after physicists in the world almost overnight. And Michael Green, his partner in this work, deserves enormous credit too. Green had come to string theory from a background in particle physics, and he brought a kind of careful, methodical approach that complemented Schwartz's deep intuition. Their collaboration was genuinely equal. Both of them contributed essential ideas to the anomaly cancellation proof. Green would go on to become the Lucasian Professor of Mathematics at Cambridge, the same chair once held by Newton and later by Stephen Hawking. Not a bad trajectory for someone who spent years working on a theory most people thought was a dead end. So now it's late 1984, early 1985, and the field is exploding. But here's the thing, and this is one of those complications that makes string theory so fascinating and so maddening. It turns out there isn't just one superstring theory. There are five distinct, mathematically consistent superstring theories, all living in 10 dimensions, all incorporating supersymmetry, all free of anomalies. And they're genuinely different from each other. Let me walk you through them, because understanding this multiplicity matters for where the story goes next. The first two are called Type 2A and Type 2B. These are theories of closed strings only, loops, no open endpoints. They differ in the way the supersymmetry is organized. In Type 2A, the left-moving and right-moving vibrations on the string have opposite chirality, opposite-handedness, if you like. In Type 2B, they have the same chirality. It sounds like a minor technical distinction, and in some ways it is, but it leads to genuinely different physics. Type 2A is non-chiral, meaning it treats left and right symmetrically, while Type 2B is chiral. Since our actual universe is chiral, the weak nuclear force distinguishes between left-handed and right-handed particles. This distinction matters. Then there's Type 1, which is the theory Green and Schwartz originally studied. Type 1 includes both open and closed strings, and it has the SO32 gauge group. It's the theory where the anomaly cancellation was first demonstrated. Type 1 strings can have their endpoints attached to various objects, which becomes important later in the story. And then there are two heterotic string theories. The word heterotic comes from the Greek word for hybrid, and these theories are genuinely strange and wonderful. They were discovered in 1985 by a group that became known as the Princeton String Quartet: David Gross, Jeffrey Harvey, Emil Martinek, and Ryan Rohm. What makes heterotic strings so unusual is that they're a hybrid of two completely different kinds of string theory. The left-moving vibrations on the string are described by the old 26-dimensional bosonic string theory, the one with the tachyon problem, the one that seemed like a dead end. And the right-moving vibrations are described by the 10-dimensional superstring. So you have this Frankenstein's monster of a theory, where different parts of the string are living in different numbers of dimensions. Now, you might think that sounds insane. How can the left-moving and right-moving vibrations on the same string live in different numbers of dimensions? Here's the trick. The extra 16 dimensions that the left movers need, the difference between 26 and 10, get compactified on a very special kind of lattice. And the geometry of that lattice determines the gauge group of the theory. For one choice, you get E 8 times E8. For the other, you get SO32. So there are two heterotic theories, and the E 8 times E8 version is the one that Witten and his collaborators had identified as particularly promising for containing the standard model. 5 theories, all mathematically consistent, all living in 10 dimensions, all incorporating gravity and quantum mechanics, and nobody knows which one, if any, describes our universe. This is both exhilarating and deeply troubling. On the one hand, the fact that there are 5 consistent quantum theories of gravity is remarkable. Before string theory, we had 0. On the other hand, a theory of everything is supposed to be unique. It's supposed to give you one framework, one set of equations, one answer. Having 5 candidates feels like having 5 maps to the same treasure, each showing different landmarks. Either 4 of them are wrong, or there's something deeper going on that connects them all. And here's where we need to talk about what these theories actually predict. Because this is where the rubber meets the road. Or rather, where the rubber fails to meet the road. Because one of the persistent criticisms of string theory, even during the euphoria of the first superstring revolution, is that it's extraordinarily difficult to extract concrete, testable predictions from it. The problem is partly the extra dimensions. When you compactify 6 dimensions on a Calabi-Yau manifold, the shape of that manifold determines the low-energy physics you see in 4 dimensions, the particle masses, the coupling constants, the number of generations of matter. But there are tens of thousands of known Calabi-Yau manifolds, and each one gives different physics. So which one does nature choose? String theory, at least as it stood in the mid-1980s, doesn't tell you. It gives you a framework, a set of rules, a menu of possibilities, but it doesn't point to one specific item on the menu and say, "That's your universe." This is genuinely different from how other theories in physics work. When Maxwell wrote down his equations of electromagnetism, they made specific predictions. The speed of light, the existence of radio waves, that could be checked. When Einstein formulated general relativity, it predicted the precise amount by which starlight would bend around the sun, and Arthur Eddington went out and measured it. String theory, by contrast, makes its most dramatic predictions at energy scales, so far beyond what any conceivable experiment could reach, that direct testing seems almost impossible. The characteristic energy scale of string theory is the Planck energy, about 10 to the 19th giga-electron volts. The most powerful particle accelerator ever built, the Large Hadron Collider, reaches about 10 to the 4th giga-electron volts. That's a gap of 15 orders of magnitude. It's like trying to study individual atoms using a magnifying glass designed for reading newspapers. So even as hundreds of physicists rushed into string theory in the mid-1980s, there was this nagging question underneath all the excitement. How would we ever know if it's right? Some people found this deeply unsettling. Others argued that mathematical consistency and elegance were themselves powerful guides, that a theory this beautiful and this constrained had to be telling us something true about nature, even if we couldn't test it directly yet. This tension between beauty and testability has never gone away. It's still one of the most heated debates in all of physics. But let's set that aside for now, because the story of the late 1980s and early 1990s is about something else entirely. It's about what happens when a field grows rapidly and then hits a wall. Because after the initial euphoria of the first superstring revolution, progress slowed. The easy problems got solved quickly, and what remained were the hard ones. Really hard ones. And the hardest of all was this. String theory, as it was formulated, was a perturbative theory. That means it worked by calculating things as a series of successive approximations. First approximation, second approximation, third approximation, each one a small correction to the last. This is how most of quantum field theory works, and it's incredibly powerful when the forces involved are weak. But when forces are strong, when the coupling constant is large, perturbation theory breaks down completely. The successive approximations stop getting smaller and start getting bigger, and the whole calculational framework falls apart. And here's the thing. Some of the most important questions in physics involve strong coupling. The confinement of quarks inside protons and neutrons is a strong coupling phenomenon. The behavior of black holes at the quantum level almost certainly involves strong coupling. The very question of which string theory vacuum nature selects might depend on strong coupling dynamics. So having a theory that only works at weak coupling is like having a flashlight that only works in well-lit rooms. Useful, sure, but it's not going to help you find what you're looking for in the dark. Throughout the late 1980s and into the early 1990s, physicists struggled with this limitation. They developed increasingly sophisticated perturbative techniques. They explored the mathematical structure of Calabi-Yau compactifications in extraordinary detail. They discovered beautiful connections between string theory and pure mathematics. Mirror symmetry, for instance, which showed that two completely different Calabi-Yau manifolds could give rise to the same physics, a result that stunned mathematicians and led to solutions of long-standing problems in algebraic geometry. But the fundamental barrier of strong coupling remained. And then, in 1995, something happened that changed everything again. Edward Witten gave a talk at a conference at the University of Southern California that is still talked about in hushed tones by people who were there. And what he proposed was so audacious, so sweeping, that it fundamentally redrew the map of string theory itself. Witten stood in front of a room full of the best string theorists on the planet and essentially told them that the 5 theories they had been studying for a decade were not 5 separate theories at all. They were 5 different windows into a single, deeper structure, something he called M theory. Now, let that sink in for a moment. For years, the existence of 5 consistent superstring theories had been a genuine embarrassment. If string theory was supposed to be the unique theory of everything, why were there 5 versions of it? That's like saying you found the one true map of the world, and then someone points out, you actually have 5 different maps, and they don't all agree. It was a real problem. People had tried to argue that maybe one of the 5 was the right one, and the others were mathematical curiosities. But there was no principled way to choose. Each of the 5 was internally consistent. Each had its own elegance, and nobody could prove any of them wrong. What Witten proposed was that this apparent embarrassment was actually a clue. The 5 theories weren't competitors. They were different limiting cases of a single underlying theory. The way that ice, liquid water, and steam aren't 3 different substances, but 3 phases of the same substance viewed under different conditions. Each of the 5 string theories, Witten argued, corresponds to a particular corner of a larger parameter space. When you dial the coupling constant to particular values, when you compactify dimensions in particular ways, you recover one or another of the 5 familiar theories. But the full theory, M theory, lives in the middle of that parameter space, in a regime that none of the 5 perturbative descriptions can fully capture. And here's one of the most striking details. M theory doesn't live in 10 dimensions. It lives in 11. Remember how the bosonic string needed 26 dimensions, and then the superstring brought that down to 10? Well, Witten was saying that the true theory actually needs 11 space-time dimensions, 10 of space and 1 of time. This wasn't entirely out of nowhere, actually. Back in the 1970s and 1980s, there had been a lot of work on something called 11-dimensional supergravity, which is the highest dimensional version of supergravity that makes mathematical sense. Supergravity is essentially the classical limit of what a quantum theory of gravity with supersymmetry would look like. And in 11 dimensions, it has a particular uniqueness and beauty. But people had moved away from it because it seemed like you couldn't build a consistent quantum theory in 11 dimensions using strings. Strings naturally live in 10. So 11-dimensional supergravity was treated as a curiosity, a mathematical side road. Witten's insight was that 11-dimensional supergravity isn't a side road at all. It's the low energy limit of M theory, the theory you get when you zoom out far enough that the fine quantum details blur away and you're left with the classical gravitational physics. And the reason strings seem to live in 10 dimensions is that you're always looking at M theory from one of its 5 corners, where one of the 11 dimensions has become very small or has been wrapped up in a way that hides it. When that hidden dimension is tiny, you see 10-dimensional string theory. When it opens up, you see the full 11-dimensional picture. So what is M theory exactly? And this is where things get beautifully, maddeningly honest. Nobody knows the full formulation. Witten proposed it, sketched its outlines, showed that it must exist based on a web of mathematical consistencies and dualities, but he didn't write down the equations. To this day, more than a quarter-century later, the complete formulation of M theory remains unknown. It's one of the great open problems in theoretical physics. We know a lot about its properties. We know its low energy limit. We know how it connects to the 5-string theories. But the full, non-perturbative definition of M theory, the master equation, if you want to think of it that way, hasn't been found. It's like knowing the shadow of something from 5 different angles and being able to deduce a great deal about its shape, but never quite being able to see the object itself directly. And what does the M stand for? Witten himself has been deliberately coy about this. He suggested it could stand for master, or mother, or membrane, or mystery, or magic. He once said the M stands for whatever you'd like it to stand for, which is either charmingly humble or slightly maddening, depending on your temperament. But the membrane interpretation gives you a real physical hint about what's new in M theory, because one of the key ingredients is that strings are no longer the only fundamental objects. In 10-dimensional string theory, the fundamental thing is a 1-dimensional string, a loop or a strand. But in 11-dimensional M theory, there are also membranes. Specifically, there are 2-dimensional membranes, called M2 branes, and 5-dimensional membranes, called M5 branes. These are higher dimensional generalizations of a string. A string sweeps out a 2-dimensional surface as it moves through space-time, its world sheet. An M2 brane sweeps out a 3-dimensional volume. An M5 brane sweeps out a 6-dimensional volume. And when you compactify one of the 11 dimensions, when you curl it up into a tiny circle, an M2 brane that wraps around that circle looks, from the 10-dimensional perspective, exactly like a string. So strings themselves emerge from something more fundamental. They're membranes viewed from a lower dimensional perspective. This is where the concept of branes, short for membranes, really enters the story in a big way. And it's worth pausing here because branes turn out to be enormously important, not just as abstract mathematical objects, but as tools for understanding real physics. In the mid-1990s, Joe Polchinski at the University of California, Santa Barbara, made a crucial discovery about a particular kind of brane called a D-brane. The D stands for Dirichlet, after the 19th century mathematician Peter Gustav Lejeune Dirichlet. And here's why. In string theory, when you have an open string, a string with 2 endpoints rather than a closed loop, you need to specify what happens at those endpoints. There are different possible boundary conditions. One option, called Neumann boundary conditions, lets the endpoints move freely. But another option, Dirichlet boundary conditions, pins the endpoints to a specific location or a specific surface. A D-brane is precisely that surface. It's the object on which open string endpoints are stuck. Now, this might sound like a technicality, but Polchinski showed in 1995 that D-branes are dynamical objects in their own right. They have mass. They have charge. They interact with gravity. They're not just passive surfaces. They're physical things, as real within the theory as the strings themselves. and they come in various dimensions. A D0 brane is a point particle. A D1 brane is a one-dimensional string. A D2 brane is a two-dimensional surface, and so on, all the way up to D9 branes that fill 9 spatial dimensions. The type of D branes that exist depends on which of the 5 string theories you're working in. Type 2A has even-dimensional D branes, D0, D2, D4, D6, D8. Type 2B has odd-dimensional ones, D1, D3, D5, D7, D9. Type 1 has its own set, and each of these branes has specific physical properties that can be calculated precisely. Here's the thing that made D branes so revolutionary. They gave physicists a non-perturbative tool. Remember the whole problem of strong coupling? Perturbation theory breaks down when forces are strong. Well, D branes are inherently non-perturbative objects. Their mass is inversely proportional to the string coupling constant, so when the coupling is weak, D branes are incredibly heavy and essentially invisible, which is why they were missed in the early perturbative analyses. But when the coupling becomes strong, D branes become light and important. They're the objects that dominate the strong coupling physics. In a very real sense, D branes are the flashlight that works in the dark. And this connects to the web of dualities that Witten and others uncovered, which is really the mathematical backbone of the second superstring revolution. There are 2 main types of duality you should know about. The first is called T-duality, and it's been known since the late 1980s. T-duality says that if you compactify a dimension on a circle of radius r, the physics is identical to compactifying on a circle of radius 1 over r in appropriate units. Think about what that means. A tiny curled-up dimension and a huge curled-up dimension give you the same physics. This is profoundly strange and has no analog in ordinary physics. It's a uniquely stringy phenomenon, arising because strings can wind around compact dimensions. A point particle can't do that, but a loop of string can wrap around a circle like a rubber band around a pencil. And the energy associated with that winding exactly trades off with the energy of momentum modes when you swap r for 1 over r. T-duality connects the 2 Type 2 theories to each other. Type 2A compactified on a circle of radius r is equivalent to Type 2. B compactified on a circle of radius 1 over r. It also connects the 2 heterotic theories to each other. So already, the 5 theories start to look less independent. But the really powerful duality is S-duality, and this is the one that directly addresses the strong coupling problem. S-duality says that a string theory at strong coupling is equivalent to another string theory, or sometimes the same theory, at weak coupling. So if you crank up the coupling constant in one theory, until perturbation theory breaks down and you can't calculate anything, S-duality tells you that you can instead switch to a dual description, where the coupling is weak and perturbation theory works perfectly. It's like having a dictionary that translates an impossible problem into a solvable one. Type 2, B-string theory, for instance, is S-dual to itself. It at strong coupling looks like itself at weak coupling, but with strings and D1 branes swapping roles. Type 1 string theory at strong coupling is equivalent to the SO32 heterotic string at weak coupling, which is remarkable because these 2 theories look completely different at weak coupling. One has open and closed strings, the other has only closed strings. They have different worldsheet structures. But they're secretly the same theory viewed from opposite ends of the coupling spectrum. And the E 8 times E 8 heterotic string at strong coupling grows an 11th dimension and becomes M theory. So now you can see the picture that emerged from Witten's 1995 proposal and the flurry of work that followed. The 5 string theories and 11-dimensional supergravity are all connected by this web of dualities: T-duality, S-duality, and combinations of both. They're not 5 theories plus 1. They're 6 faces of a single jewel, and that jewel is M-theory. And even though we can't see the jewel directly, we don't have its fundamental formulation, we can infer an enormous amount about it from the consistency of the connections between its faces. This was the second superstring revolution, and it unfolded with breathtaking speed through 1995 and 1996. Papers were appearing on the arXiv preprint server almost daily. People who had been working on one particular string theory suddenly found their results connecting to work done by people in completely different corners of the field. It was one of those rare moments in science where a whole community simultaneously realizes that the landscape is much larger and more connected than anyone had imagined. And it was in this heady atmosphere that one of the most celebrated results in the entire history of string theory was achieved. A result that, for many physicists, remains the single most compelling piece of evidence that string theory is on the right track, even in the absence of experimental confirmation. It involved black holes, and it came from a young physicist named Andrew Strominger and his collaborator Kamran Vafa, both at Harvard. And what they did, in a 1996 paper that is still one of the most cited in the field, was they counted the microscopic states of a very particular kind of black hole and showed that the number they got matched exactly, not approximately, not in the right ballpark, but precisely, digit for digit. The entropy predicted by Stephen Hawking's famous formula from 1975. And to understand why that was such a big deal, you need to appreciate just how strange and troubling the problem of black hole entropy had been for over 2 decades. So let's back up for a moment. In the early 1970s, Jacob Bekenstein, who was then a graduate student working under John Wheeler at Princeton, proposed something radical. He suggested that black holes have entropy. Now, entropy is one of those concepts that sounds abstract, but is actually very concrete. It's a count. Specifically, it's related to the number of microscopic ways you can arrange the internal parts of a system while still having it look the same from the outside. Think of it this way. Imagine you have a box of gas, and from the outside you can measure its temperature, its pressure, its volume. But inside, the individual molecules could be arranged in an astronomical number of different configurations that would all give you the same temperature, pressure, and volume. The logarithm of that number of configurations is, roughly speaking, the entropy. It tells you how much hidden information is inside. Bekenstein's idea was that black holes, despite looking very simple from the outside, described by just their mass, charge, and spin, must have an enormous amount of hidden internal structure, and therefore an enormous entropy. And he proposed that this entropy was proportional to the area of the event horizon, not the volume, which is what you might naively expect, but the area. That's already strange. It's as if all the information about what's inside a room is somehow encoded on the walls rather than in the interior. Hawking initially resisted this idea, but then in 1974 and 1975, through his own brilliant calculation combining quantum field theory with general relativity in a semi-classical approximation, he showed that black holes actually radiate. They emit thermal radiation, what we now call Hawking radiation, and they have a definite temperature. And once you accept that a black hole has a temperature, thermodynamics forces you to assign it an entropy, And that entropy turns out to be exactly what Bekenstein had proposed. The formula is beautifully simple. The entropy equals 1/4 of the area of the event horizon, measured in Planck units. It's called the Bekenstein-Hawking entropy, and it's one of the most profound equations in all of physics because it ties together gravity, quantum mechanics, and thermodynamics in a single expression. But here's the thing that haunted physicists for 20 years after Hawking wrote it down. The formula tells you the answer. It tells you the number, but it doesn't tell you what's being counted. Remember, entropy is supposed to be the logarithm of the number of microstates. So if a black hole has this enormous entropy, there should be some microscopic degrees of freedom, some tiny internal constituents that you can arrange in exactly that many ways. But what are they? In ordinary thermodynamics, the microstates are molecular configurations. For a black hole, nobody knew. General relativity describes the black hole as a smooth, featureless geometry. There's no obvious place to put the microstates. The event horizon is not a physical membrane. It's just a boundary in space-time. The singularity at the center is a place where the theory breaks down. So, where does the information live? What are you counting? This was the black hole entropy puzzle, and it was widely regarded as one of the deepest problems in theoretical physics. Any serious candidate for a quantum theory of gravity would need to answer it. If your theory can't explain where the Bekenstein-Hawking entropy comes from, if it can't provide the microstates, then it's not really a complete theory of quantum gravity. And that's exactly what Strominger and Vafa did in January of 1996. Now, they were clever about which black hole they chose. They didn't try to tackle the most general, astrophysically realistic black hole, a rotating, uncharged black hole like the ones we observe in nature. That would have been far too difficult. Instead, they worked with a very specific, highly symmetric, extremal black hole in 5 dimensions. Extremal means the black hole carries the maximum possible charge for its mass. It's a kind of limiting case where the gravitational attraction and the electromagnetic repulsion are perfectly balanced, and the Hawking temperature drops to 0. 5 dimensions, because certain string theory calculations are more tractable there. And the black hole carried 3 different types of charge, which in string theory language corresponded to different configurations of d-branes. Here's where Polchinski's d-branes, which we were just talking about, become absolutely essential. Strominger and Vafa constructed their black hole by wrapping d-branes around the compact dimensions of the internal space. Specifically, they used d1 branes and d5 branes in type 2b string theory, wrapped around a compact 5-dimensional manifold, a 4 torus times a circle to be precise, along with momentum modes flowing along one of the compact directions. These 3 ingredients, d1 branes, d5 branes, and momentum, gave the black hole its 3 charges. And here's the beautiful trick. At weak string coupling, when the gravitational force is feeble, this collection of d-branes doesn't form a black hole at all. It's just a configuration of branes sitting in flat space-time, and you can study it using the ordinary tools of quantum field theory, specifically a 2-dimensional conformal field theory that lives on the intersection of the branes. In that regime, you can count the states. You can literally enumerate the number of quantum mechanical configurations of the open strings stretching between the d1 branes and d5 branes with a given amount of momentum. It's a hard counting problem, but it's a well-defined one, and it uses techniques from mathematics, modular forms, partition functions, that have been understood since the work of Ramanujan and Hardy in the early 20th century. Now, you might be thinking, wait, if the branes don't form a black hole at weak coupling, How can you compare the result to the Bekenstein-Hawking entropy, which is a property of a black hole at strong coupling? And that's exactly the right question to ask. The answer relies on a deep property of these extremal, supersymmetric configurations. The number of states is protected. It doesn't change as you dial up the coupling from weak to strong. Supersymmetry acts like a shield, preventing quantum corrections from altering the count, so you can count the states in the easy regime, where there's no black hole and you have full computational control, and then you can trust that the answer remains valid in the hard regime, where the same configuration has collapsed into a black hole. And when Strominger and Waffe did the counting, the result was extraordinary. The logarithm of the number of microstates came out to exactly 1/4 of the horizon area. Exactly. The Bekenstein-Hawking formula was reproduced from a microscopic calculation for the first time in history. Think about what that means for a second. For 20 years, physicists had this formula that told them black holes carry entropy, but nobody could explain where that entropy came from. And then string theory, this framework that people criticized for being untestable, for being too mathematical, for having no connection to the real world. String theory provided the answer. It told you what the microstates are. They're configurations of D-branes and open strings. The information isn't stored in some mysterious way at the singularity or smeared across the horizon in some hand-wavy sense. It's stored in the quantum states of the brain system. The entropy is a count of string-theoretic microstates, and the count matches perfectly. This result electrified the community. It was extended rapidly to near-extremal black holes, to black holes with different charges, to black holes in 4 dimensions, to rotating black holes. In each case where the calculation could be done, the microscopic counting agreed with the Bekenstein-Hawking formula. Not just the leading term, but in many cases the sub-leading corrections as well. And this wasn't a case of fitting parameters. There were no free knobs to adjust. The agreement was a genuine prediction, emerging from the mathematical structure of string theory itself. Now, I should be honest with you. These are all very special black holes. They're extremal or near-extremal. They're typically supersymmetric, and they exist in spacetimes with extra dimensions and specific compactification geometries. Nobody has yet managed to do the full microstate counting for a plain Schwarzschild black hole, the simplest, most astrophysically relevant kind, with no charge and no angular momentum. That remains an open problem, so the skeptic can reasonably say, "You've solved a toy version of the problem, but you haven't solved the real one." And that's fair. But the fact that string theory can solve even the toy version and get the exact right answer with no adjustable parameters is something no other approach to quantum gravity had achieved at that time. It remains one of the crown jewels of the field. And the black hole story didn't stop there. It opened up a whole cascade of ideas about the nature of quantum gravity, information, and space-time itself. One of the most profound outgrowths was the holographic principle and, eventually, the ADS/CFT correspondence. Arguably, the single most important theoretical development in fundamental physics since string theory itself. And this came from a physicist we've already mentioned in passing, Juan Maldacena, who in 1997, just a year after Strominger and Waffe's paper, proposed something so audacious that it took the community years to fully absorb it. What Maldacena conjectured was a precise mathematical equivalence, a duality, between a gravitational theory in a specific curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime, specifically he proposed the type 2b superstring theory on a 5-dimensional anti-de Sitter space. Times a 5-sphere is exactly equivalent to a 4-dimensional supersymmetric Yang-Mills gauge theory, a type of quantum field theory closely related to the theories that describe the strong and weak nuclear forces living on the 4-dimensional boundary of the anti-de Sitter space. Let me unpack that a little, because it's genuinely one of the wildest ideas in all of physics. Anti-de Sitter space, or ADS, is a solution to Einstein's equations with a negative cosmological constant. It's a space-time that's curved in a very specific way. It has a kind of hyperbolic geometry, and it has a boundary at spatial infinity. The boundary is 1 dimension lower than the bulk. So if the bulk is 5-dimensional, the boundary is 4-dimensional. And what Maldacena was saying is that everything that happens in the 5-dimensional gravitational bulk, strings vibrating, black holes forming and evaporating, gravitons scattering, all of it is completely and exactly described by a quantum field theory that lives on the 4-dimensional boundary and contains no gravity at all. This is holography. The bulk physics is like a hologram projected from the boundary. All the information about the interior of the spacetime is encoded on its boundary in one fewer dimension. And if that reminds you of Bekenstein's observation that black hole entropy scales with area rather than volume, well, it should. That was one of the key hints that led people toward holographic thinking in the first place. Gerard 't Hooft and Leonard Susskind had both speculated about a holographic principle in the mid-1990s, but Maldacena gave it a concrete, mathematically precise realization. The ADS/CFT correspondence, also called the Maldacena conjecture, or gauge/gravity duality, has never been proven in the strict mathematical sense, but the evidence for it is overwhelming. Thousands of calculations have been done on both sides of the duality, and every single one that can be checked has matched. It's become one of the most productive tools in theoretical physics, used not just by string theorists, but by people working on nuclear physics, condensed matter physics, quantum information, and even fluid dynamics. And here's what's really remarkable about it. It turns the problem of quantum gravity into a problem in ordinary quantum field theory, and vice versa. If you have a hard problem on one side, you can translate it to the other side, where it might be easy. Strong coupling in the gauge theory maps to weak coupling in the gravity theory, and the other way around. It's like having a dictionary between two languages, where some things are easier to say in one language than the other. But the implications go even deeper than computational convenience. If ADS/CFT is correct, and almost everyone in the field believes it is, then it tells you something astonishing about the nature of spacetime. It tells you that spacetime, including the dimension of depth, the radial direction into the bulk, is not fundamental. It emerges. It's built up from the entanglement structure of the boundary quantum field theory. The geometry of the interior is encoded in the patterns of quantum entanglement on the boundary. This idea has been made increasingly precise over the past 2 decades through the work of Mark van Ramsdonk, Shinsei Ryu, Tadashi Takayanagi, and many others. The Ryu-Takayanagi formula proposed in 2006 gives a beautiful geometric prescription. The entanglement entropy of a region on the boundary equals the area of a minimal surface in the bulk that is anchored to the boundary of that region. It's the Bekenstein-Hawking formula generalized, and it directly connects the fabric of space-time to quantum information. So by the late 1990s, String theory had gone from being a somewhat speculative framework for quantum gravity to something far richer and more interconnected. It had provided a microscopic explanation for black hole entropy. It had given birth to the holographic principle in a precise form. It had unified the 5 superstring theories into a single framework, and through ADS/CFT, it had opened up an entirely new way of thinking about the relationship between gravity and quantum mechanics, one where space-time itself might be an emergent phenomenon, woven from quantum entanglement. But there was a shadow gathering at the edges of all this triumph, a problem that had been lurking since the earliest days of compactification and that, in the early 2000s, would explode into what many considered an existential crisis for the theory. It had to do with those extra dimensions we talked about earlier, the ones that get curled up into tiny Calabi-Yau shapes. Remember how we said there are tens of thousands of known Calabi-Yau manifolds, each giving different physics? Well, the situation turned out to be much, much worse than that, because each Calabi-Yau manifold doesn't just come in one flavor. Each one has what are called moduli, parameters that describe its size, its shape, the way different cycles within it are stretched or squeezed. Think of it like this. Imagine you have a donut, a simple torus. Even that single shape has moduli. You can make the donut fatter or thinner. You can stretch the hole wider or pinch it tighter. Each of those configurations is technically a different geometry, and in string theory, different geometry means different physics, different particle masses, different coupling constants, different values for the cosmological constant. Now, scale that up from a simple donut to a 6-dimensional Calabi-Yau manifold with hundreds of topological features, hundreds of holes and cycles and surfaces threading through each other in ways that are genuinely impossible to visualize. Each of those features has its own modulus, its own dial you can turn, and the number of distinct ways you can set all those dials, the number of distinct vacuum states the theory can land in, is not thousands, it's not millions. The estimates that emerged in the early 2000s, particularly through the work of Raphael Bousso and Joseph Polchinski in 2000, and then Shamit Kachru, Renata Kalosh, Andrei Linde, and Sandip Trivedi in 2003, that famous KKLT paper, suggested the number of possible vacuum states in string theory could be something like 10 to the 500, 10 to the 500. Let that number sit with you for a moment. The number of atoms in the observable universe is roughly 10 to the 80. 10 to the 500 is so incomprehensibly larger than that, it makes the number of atoms in the universe look like a rounding error. And each one of those vacua, each one of those 10 to the 500 configurations corresponds to a different possible universe with different physical laws, different particle content, different values for things like the strength of gravity or the mass of the electron. This collection of possibilities became known as the string theory landscape, and the person who really crystallized the term and the concept was Leonard Susskind around 2003. Susskind, who you'll remember, was one of the original co-discoverers of string theory back in the late 1960s, had been thinking about this problem deeply, and he saw both the crisis and, controversially, a possible way to reframe it. But let's talk about why it's a crisis first. The whole dream of string theory, from the very beginning, was unification. One theory, one framework, one set of equations that would uniquely determine the laws of physics. The hope was that when you finally worked out all the mathematics, the theory would spit out our universe, our particles, our forces, our constants, as the unique solution. or at least as one of a very small number of solutions. That was the promise. That was what made people willing to spend decades on a theory with no direct experimental evidence. The payoff was supposed to be that the theory would be so constrained, so rigid in its mathematical structure, that it could only describe one possible world, and that world would be ours. The landscape shattered that dream. Instead of one solution, you had 10 to the 500. Instead of the theory telling you why the electron has the mass it does, or why there are 3 generations of quarks and leptons, or why the cosmological constant has the absurdly tiny value we observe. Instead of answering those questions, the theory seemed to be saying, well, all those values are possible. Your universe is just one island in an unfathomably vast archipelago of possibilities. And here's where it gets really contentious. Susskind and others proposed that maybe this wasn't a bug, maybe it was a feature. Their argument drew on an idea from cosmology: eternal inflation. The basic picture is that our Big Bang might not have been the only one. In the theory of eternal inflation, which had been developed by Alan Guth, Andre Linde, and others starting in the early 1980s, the inflationary process that stretched our early universe doesn't stop everywhere at once. It keeps going in some regions, spawning new bubble universes, each of which might land in a different vacuum state from the landscape. So you'd get a multiverse, a vast, perhaps infinite collection of pocket universes, each with its own version of physics, each corresponding to a different point in the string theory landscape. Now, if that's the case, then asking why our universe has the particular physical constants it does is a bit like asking why you happen to live on a planet that's the right distance from its star for liquid water. It's not that there's some deep reason the Earth had to be at this distance. It's that there are billions of planets, and you naturally find yourself on one of the ones that can support your existence. This style of reasoning is called the anthropic principle, and it has a long and somewhat uncomfortable history in physics. The anthropic argument for the cosmological constant goes like this. The cosmological constant, the energy density of empty space, the thing that's making the expansion of the universe accelerate, has a measured value of roughly 10 to the minus 122 in natural units. That number is absurdly small. If you tried to calculate it from quantum field theory, you'd get a number that's 10 to the 120 times too big. This is sometimes called the worst prediction in the history of physics. For decades, physicists assumed some unknown symmetry or mechanism would drive the cosmological constant to exactly 0. But then, in 1998, 2 teams, the Supernova Cosmology Project, led by Saul Perlmutter, and the High Z Supernova Search Team, led by Brian Schmidt and Adam Rees, discovered that the expansion of the universe is accelerating, meaning the cosmological constant is not 0. It's tiny, but it's there, and nobody could explain why. Steven Weinberg, the Nobel laureate, had actually made a prescient anthropic prediction back in 1987. He argued that if the cosmological constant were much larger than a certain value, galaxies could never have formed, because the accelerating expansion would have torn matter apart before it could clump together. So if you're going to find yourself in a universe at all, if you're going to be around to ask the question, the cosmological constant has to be small. And if there's a landscape of possible values, you'd expect to find yourself in a universe where it's small enough for structure to form, but not necessarily 0. The observed value fits this anthropic window surprisingly well. So the landscape plus eternal inflation, plus the anthropic principle, offered a potential explanation for one of the deepest fine-tuning puzzles in physics. But the cost was enormous. You had to give up on the idea that string theory uniquely predicts our universe. You had to accept that the theory describes a multiverse, and that the particular physics we observe is partly a matter of environmental selection, cosmic accident, if you want to be blunt about it. This did not go over well with a lot of physicists. And honestly, you can understand why. If a theory can describe 10 to the 500 different universes, and you can always say, well, we just happen to be in this one, then what exactly does the theory predict? How could you ever falsify it? This is the criticism that has dogged string theory most persistently, and it's a serious one. David Gross, who shared the 2004 Nobel Prize for the discovery of asymptotic freedom in quantum chromodynamics, was one of the most vocal critics of the anthropic turn. He called it a dangerous retreat from the traditional goals of physics. Peter Woit, a mathematician at Columbia, published a book in 2006 called Not Even Wrong, arguing that string theory had become unfalsifiable and therefore unscientific in the Popperian sense. Lee Smolin, a theoretical physicist at the Perimeter Institute, published The Trouble with Physics the same year, making similar arguments. The string theory community was genuinely divided. Some embraced the landscape and the multiverse as the natural consequence of the mathematics. Others saw it as a sign that something had gone deeply wrong, that perhaps the theory needed to be constrained further, or that the right vacuum, our vacuum, could still be identified through some principle not yet understood. This idea that there might be some criterion, some selection mechanism within the theory that picks out our universe from the landscape is sometimes called the swampland program, and it's become one of the most active areas of research in recent years. The basic idea, championed by Kumrun Vafa of Harvard starting around 2005, is to figure out which of those 10 to the 500 vacua are actually consistent, which ones belong to the landscape of genuine string theory solutions, and which ones look like they might work but actually don't, which ones belong to the swampland. Maybe, the thinking goes, when you properly account for all the consistency requirements of quantum gravity, the landscape shrinks dramatically. Maybe the swampland is actually much bigger than the landscape, and the constraints are much tighter than they appear. And here's what's genuinely interesting about the swampland program. It has produced concrete, testable conjectures. Vafa and his collaborators have proposed specific conditions that any low-energy effective theory must satisfy in order to be compatible with quantum gravity. Some of these conjectures, if true, would have observable consequences. For instance, one version of the swampland conjecture places constraints on the behavior of dark energy, potentially ruling out a simple cosmological constant in favor of a dynamical field called quintessence. That's the kind of thing you could, in principle, test with cosmological observations. The Dark Energy Spectroscopic Instrument, or DESI, which began its survey in 2021, is collecting data that could bear on exactly this question. So the landscape crisis, paradoxically, may end up pushing string theory toward testability rather than away from it. But let's step back from the landscape for a moment and talk about something that's been happening in parallel, something that connects back to ADS/CFT and the holographic principle, but takes it in a direction nobody expected. Because one of the most remarkable developments of the past 15 years or so has been the way string theory ideas have migrated out of high-energy physics and into completely different fields. Fields where they've actually been used to make concrete, quantitative predictions that can be checked against experiment. The most famous example is the application of ADS/CFT to the quark-gluon plasma. Here's the setup. At the relativistic heavy ion collider, RHIC, at Brookhaven National Laboratory on Long Island, and later at the Large Hadron Collider at CERN. Physicists have been smashing heavy atomic nuclei together at nearly the speed of light. Gold nuclei at RHIC, lead nuclei at the LHC. When these nuclei collide, the temperatures and densities become so extreme that the protons and neutrons essentially melt. The quarks and gluons that are normally confined inside protons break free and form a new state of matter called the quark-gluon plasma. This is the stuff that filled the universe in the first few microseconds after the Big Bang. Now, the surprise was that this quark-gluon plasma didn't behave the way people expected. The naive expectation, based on a property of quantum chromodynamics called asymptotic freedom, the very thing David Gross won his Nobel Prize for, was that at very high temperatures, quarks and gluons should become weakly interacting. They should behave almost like a gas of free particles. But that's not what RHIC observed. Instead, the quark-gluon plasma behaved like a nearly perfect liquid, one of the most perfect fluids ever observed, in fact. It flowed with almost no viscosity, responding to disturbances collectively, like a single coherent substance rather than a collection of independent particles. The problem was that the standard theoretical tools, perturbative quantum chromodynamics, couldn't handle this regime very well. The coupling was too strong. The interactions were too intense. And this is exactly the kind of situation where ADS/CFT shines, because the duality maps a strongly coupled quantum field theory to a weakly curved gravitational system, which is much easier to calculate with. In 2001, before the RHIC results were even fully analyzed, Polycastro, Sun, and Starinets used ADS/CFT to calculate the ratio of shear viscosity to entropy density for the strongly coupled plasma described by the boundary theory. They found a remarkably simple and universal result, 1/4 pi in natural units. And when the experimental data from RHIC came in, the measured viscosity of the quark-gluon plasma was strikingly close to this value. Not exact. The real-world theory isn't exactly the same as the supersymmetric theory in the ADS/CFT calculation, but close enough to suggest that the holographic approach was capturing something real about strongly coupled fluids. This was a genuine shock. A calculation rooted in string theory and black hole physics was giving quantitatively useful results for an experiment happening in a laboratory on Long Island. The quark-gluon plasma, a real substance created in real collisions, was being described by the mathematics of black holes in five-dimensional anti-de Sitter space, and this opened the floodgates. Suddenly, people started applying ADS/CFT techniques to all sorts of strongly coupled systems. Condensed matter physics, superconductors, superfluids, even hydrodynamics. The field became known as applied holography, or ADS/CMT, when applied to condensed matter theory. It's still an active and somewhat controversial area, because the systems being modeled don't match the boundary theory of ADS/CFT exactly, so the results are more like qualitative guides than precise predictions. But the fact that a theory of quantum gravity could say anything useful about tabletop condensed matter experiments, that was something nobody had anticipated. And this points to something deeper about where string theory stands today, something that gets lost in the popular narrative of string theory can't be tested versus string theory explains everything. The reality is more nuanced and, honestly, more interesting than either extreme, because string theory has become less like a single physical theory waiting to be confirmed or refuted, and more like a vast mathematical and conceptual framework, a toolkit, almost, that keeps generating insights across multiple areas of physics. Some of those insights are directly about quantum gravity. Some are about the nature of spacetime. Some are about strongly coupled quantum systems that have nothing to do with gravity at all. And some are about pure mathematics, where string theory has led to genuinely new theorems and structures that mathematicians find valuable on their own terms. Which brings us to something that's been quietly revolutionizing our understanding of quantum gravity over the past decade or so, something that connects the holographic principle, black hole physics, and quantum information theory in ways that are still being worked out. And the story really starts with a puzzle that had been nagging people since the 1970s, the black hole information paradox. We touched on this earlier, right? Hawking showed that black holes radiate, they slowly evaporate, and the radiation that comes out appears to be perfectly thermal, perfectly random, carrying no information about what fell in. And that's a huge problem because quantum mechanics says information is never truly destroyed. Every process in quantum mechanics is, in principle, reversible. You can always reconstruct the past from the present if you have enough information. But Hawking's calculations seem to say, no, black holes are special. They eat information and spit out featureless noise. For decades, this was one of the deepest unsolved problems in theoretical physics. And string theory through ADS/CFT basically settled one side of the argument. If the holographic principle is right, if a gravitational system in the bulk is truly equivalent to a well-behaved quantum system on the boundary, then information can't be lost. The boundary theory is manifestly unitary. That's the technical term, unitarity, meaning probabilities always add up to 1 and information is always preserved. So whatever happens in the bulk, including black hole formation and evaporation, must also preserve information because it's just another description of the same physics. Hawking himself eventually conceded this point, famously in 2004. He gave a talk at a conference in Dublin and admitted he'd been wrong, that information is preserved. He even paid off a bet he'd made with John Preskill back in 1997. But here's the thing. Saying information is preserved is very different from explaining how it's preserved. The mechanism, the actual nuts and bolts of how information gets out of a black hole, remained deeply mysterious. And that's where things have gotten really exciting in the last 10 to 15 years. So let me set the stage. Around 2012 and 2013, a group of physicists, Ahmed Almheri, Donald Marolf, Joseph Polchinski, and James Sully, often called AMPS after their initials, sharpened the information paradox into something even more disturbing. They published a paper arguing that if information really is preserved during black hole evaporation, then something else has to give. Specifically, they argued that an old black hole, one that's already radiated away more than half its entropy, can't simultaneously satisfy 3 things that physicists had assumed were all true. That information is preserved, that nothing special happens at the event horizon for an infalling observer, and that the laws of physics outside the black hole look normal. You can pick any 2, but not all 3. And if you insist on information preservation and normal physics outside, then what you get at the horizon is not the smooth, uneventful crossing that general relativity predicts. Instead, you get a firewall, a wall of high-energy radiation right at the horizon that would incinerate anything trying to fall in. This was deeply shocking. The whole point of general relativity is that the event horizon of a sufficiently large black hole should be locally indistinguishable from empty space. You shouldn't notice anything special as you cross it. The equivalence principle, Einstein's foundational insight, demands this. And here were AMPS saying no, quantum mechanics might force a violent departure from that picture. The firewall paradox, as it became known, set off an enormous wave of activity. And what's fascinating is that the tools people reached for to try to resolve it came not just from string theory or general relativity, but increasingly from quantum information theory, the mathematics of entanglement, quantum error correction, computational complexity. This is where the fields started merging in ways nobody had planned. One of the key insights came from thinking carefully about entanglement entropy. How much quantum entanglement exists between different parts of a system? Remember the Ryutakayanagi formula we talked about? The one that says the entanglement entropy of a region in the boundary theory equals the area of a minimal surface in the bulk? Well, that formula works beautifully for static situations, but black holes evaporate, they're dynamic, and the original Ryutakayanagi prescription needed to be generalized. In 2014, a proposal by Engelhardt and Wall extended the formula to what are called quantum extremal surfaces, which account for not just the classical geometry, but also quantum corrections. And this turned out to be incredibly powerful, because when you apply the quantum extremal surface prescription to an evaporating black hole, something remarkable happens. Early in the evaporation, the calculation gives you a result consistent with Hawking's original answer. The entropy of the radiation just keeps growing and growing as more radiation comes out. But at a certain point, roughly when the black hole has radiated about half its entropy, a new quantum extremal surface kicks in. A different surface becomes the dominant one, and the entropy of the radiation starts to decrease. It follows what's called the Page curve, named after Don Page, who argued back in 1993 that this is exactly what should happen if information is preserved. The entropy of the radiation should go up, reach a maximum around the halfway point of evaporation, and then come back down, eventually returning to zero when the black hole is completely gone, meaning all the information has come out. Now, think about what that means. For decades, the inability to reproduce the Page curve from a gravitational calculation was the sharpest version of the information paradox. Hawking's calculation gave you ever-increasing entropy, which meant information was being lost. And now, using tools that grew directly out of string theory and holography, quantum extremal surfaces, the Ryutakayanagi framework, the whole apparatus, people were finally deriving the Page curve from the gravitational side. This was achieved in a series of landmark papers in 2019 and 2020 by groups including Pennington and separately Almheri, Engelhardt, Marolf, and Maxfield, building on earlier work by many others. The key new ingredient was something called the island formula, or the island rule. The idea is that when you calculate the entropy of Hawking radiation, you have to include not just the radiation itself, but also certain regions inside the black hole, the islands, that are quantum mechanically connected to the radiation through entanglement. It's a strange and beautiful idea. Parts of the black hole interior are, in a precise information theoretic sense, already encoded in the radiation that's already come out. The information isn't stuck behind the horizon forever. It's been gradually, subtly, almost imperceptibly leaking out, encoded in delicate quantum correlations among the Hawking radiation particles. And here's what's really wild about this. The island formula doesn't require you to know the full microscopic details of quantum gravity. It works semi-classically, using the geometry of space-time plus quantum corrections. It's a formula you can actually compute with. And it gives the right answer, the page curve, information preservation, consistency with unitarity. After 40-plus years of struggle, that felt like a genuine breakthrough. Not the final answer, not a complete theory of quantum gravity, but a concrete, calculable result that resolved one of the sharpest paradoxes in the field. And it came from the intersection of ideas that had been developing across string theory, holography, and quantum information theory for decades. This brings us to another thread that's been weaving through recent work, the idea that space-time itself might be built from quantum entanglement. We touched on this when we talked about Ryu Takayanagi and Van Ramsdonk's observation that if you reduce entanglement in the boundary theory, the bulk space-time starts to disconnect. But the idea has matured enormously since then. There's a beautiful conjecture proposed by Susskind and Maldacena in 2013, often called ER equals EPR. ER stands for Einstein-Rosen, as in Einstein-Rosen bridges, wormholes. EPR stands for Einstein-Podolsky-Rosen, the famous 1935 paper about quantum entanglement. The conjecture says that these two things, wormholes and entanglement, are actually the same phenomenon seen from different angles. Every pair of entangled particles is connected by a tiny, non-traversable wormhole. And conversely, every wormhole is a manifestation of entanglement between the quantum systems on either side. If this is right, then the geometry of space-time, the very fabric of the universe, the stage on which everything happens, is stitched together by quantum entanglement. Remove the entanglement, and space-time falls apart. Add entanglement, and space-time knits itself together. It's a radical reimagining of what space-time actually is. Not a fundamental thing, not the bedrock of reality, but an emergent phenomenon. Something that arises from deeper quantum mechanical relationships. And the tools for making this precise keep getting more sophisticated. People have connected the growth of the interior of a black hole to quantum computational complexity. Roughly, how hard it is to reconstruct the quantum state from simple operations. Susskind proposed that the volume of the region behind a black hole's horizon grows linearly for an exponentially long time, and that this growth corresponds to the increasing complexity of the quantum state on the boundary. This is called the complexity equals volume conjecture, and there's a related version called complexity equals action. These are still conjectures, not proven results, but they've spawned an entire subfield connecting quantum gravity to theoretical computer science. The idea that the geometry of space-time encodes not just information but computational difficulty. That's a genuinely new way of thinking about physics, and it emerged directly from the string theory and holography program. So where does all of this leave us? You have a field that started with Veneziano's formula for meson scattering in 1968, that was almost abandoned multiple times, that went through revolutions and crises and reinventions, and that now sits at the intersection of quantum gravity, quantum information, condensed matter physics, and pure mathematics. The landscape problem hasn't gone away. We still don't know which vacuum, if any, describes our universe. We still don't have a direct experimental test of string theory as a theory of everything. The critics who point this out aren't wrong. But the framework has produced results, real, concrete, calculable results about black hole entropy, about the information paradox, about the emergence of space-time, about strongly coupled quantum systems. And it's reshaped how physicists think about some of the deepest questions in the field, even physicists who wouldn't call themselves string theorists. There's one more piece of this story that I want to tell you about, something that connects all of these threads: the holographic principle, the information paradox, the emergence of space-time, to what might be the most ambitious question in all of physics. And that's the question of what happens when you try to build a theory of quantum gravity, not just for the interior of a black hole, not just for some carefully constructed anti-de Sitter space-time, but for the actual universe we live in. The cosmological problem, the question of quantum gravity applied to cosmology. And it's the question that, in some ways, string theory has been circling around for 50 years without fully answering. Here's what I mean. Almost everything we've talked about, ADS/CFT, the page curve calculations, the island formula, ER equals EPR, complexity equals volume, almost all of it has been worked out in anti-de Sitter space. That's the negatively curved spacetime, the one that looks like the inside of a saddle, the one with a nice boundary at infinity where you can place your holographic dual theory. And that's been incredibly productive. It's given us the clearest window we have into quantum gravity. But here's the thing. We don't live in anti-de Sitter space. Our universe, as far as we can tell from every observation we've made, the cosmic microwave background, the distribution of galaxies, the accelerating expansion discovered in 1998, our universe has a positive cosmological constant. It's expanding. It's de Sitter space or something close to it. And de Sitter space is fundamentally different from anti-de Sitter space in ways that make the whole holographic program much, much harder to apply. Think about why. In anti-de Sitter space, you have that boundary at spatial infinity. It's always there. It's a fixed, eternal stage where you can define your quantum field theory. Observables are well defined because you can ask what an observer sitting at the boundary would measure. The boundary gives you something solid to hold on to. De Sitter space doesn't have that. In de Sitter space, the boundary isn't at spatial infinity. If there's a boundary at all, it's in the far future, or maybe in the far past, and it's a space-like surface, not a time-like one. That changes everything about how you'd try to set up a holographic correspondence. You can't just take the ADS/CFT dictionary and swap in a positive cosmological constant. The whole structure of the duality depends on features that are specific to anti-de Sitter geometry. And there's a deeper conceptual issue. In de Sitter space, every observer has a cosmological horizon. You look out into the universe, and because space is expanding, there's a distance beyond which light will never reach you. You're surrounded by a horizon, kind of like a black hole horizon turned inside out. And that horizon has thermodynamic properties. It has a temperature. It has an entropy, just like a black hole. Gibbons and Hawking worked this out back in 1977. The entropy of a cosmological horizon is given by the same formula as black hole entropy, the area of the horizon divided by 4 times Newton's constant. So if you're sitting in de Sitter space, you're enclosed inside a finite region with a finite entropy. And finite entropy means a finite number of quantum states, which means, if you take this seriously, the Hilbert space of quantum gravity in de Sitter space is finite dimensional. Now, that might sound like a technical detail, but it's actually a profound problem. Quantum field theories, the kind that live on the boundary in ADS/CFT, have infinite dimensional Hilbert spaces. They have infinitely many degrees of freedom. So if the quantum gravity theory of de Sitter space has only finitely many states, it can't be dual to an ordinary quantum field theory. Whatever the holographic dual of de Sitter space is, it has to be something else, something stranger. And nobody really knows what that something is. There have been proposals. Tom Banks and Willy Fischler proposed something called the holographic space-time framework. where the fundamental objects are finite-dimensional quantum systems associated with causal diamonds, the regions of spacetime accessible to a single observer. Andy Strominger proposed a DS/CFT correspondence in 2001, where the dual theory lives on the space-like boundary in the far future and is a conformal field theory of a peculiar kind, one defined in Euclidean signature rather than the usual Lorentzian. There's been work by Eva Silverstein and others on constructing de Sitter vacua in string theory more carefully, trying to understand the landscape from a cosmological perspective. But none of these approaches has achieved anything close to the precision and richness of ADS/CFT. The de Sitter problem remains, in many ways, the biggest open problem in quantum gravity. And this connects back to the landscape in a really interesting way. Remember the 10 to the 500 vacua. Most of those vacua, or at least a huge number of them, are supposed to be de Sitter. They have positive cosmological constants. Our universe, if it's described by string theory at all, is supposed to be one of those de Sitter vacua. But the KKLT construction and its relatives, the ones that try to build explicit de Sitter vacua in string theory, have been controversial. There's been a long-running debate about whether these constructions are fully consistent. Qumran Vafa's swampland conjectures, which we talked about earlier, include one that's particularly provocative, the de Sitter conjecture, which suggests that stable de Sitter vacua might not exist in string theory at all. If that's true, it would mean our universe's accelerating expansion can't be described by a cosmological constant in the usual sense. It would have to be something else, maybe quintessence, a slowly rolling scalar field, something dynamical rather than static. You can see why this is such a charged debate. It's not just an abstract theoretical question. It's about whether string theory can describe the universe we actually observe. And the answer, honestly, is that we don't know yet. The tools aren't sharp enough. The de Sitter problem is genuinely hard, and it might require new ideas as radical as ADS/CFT was in 1997. But here's what I find quietly remarkable about all of this, and maybe this is a good place to start winding down and putting the whole story in perspective. Think about where we started. We started with Gabriele Veneziano in 1968, sitting in his office at CERN, flipping through a math handbook and recognizing that Euler's beta function could describe the scattering of mesons. That's it. That's where this all began. A young physicist and a 300-year-old mathematical function. And from that one observation, which was wrong, by the way, wrong as a theory of the strong force, from that one beautiful mistake, an entire universe of ideas unfolded. Nambu, Nielsen, and Susskind figured out that the formula described vibrating strings. Schwartz and Shirk realized the strings predicted gravity and flipped the whole enterprise from nuclear physics to quantum gravity. Green and Schwartz showed the theory was mathematically consistent, launching the first revolution. Witten unified 5 theories into M theory. Polchinski discovered D-branes. Maldacena found the holographic correspondence. Strominger and Vafa counted black hole microstates. And in the last few years, physicists have used these tools to resolve the black hole information paradox, or at least to show that the information gets out, even if we don't yet fully understand the mechanism. Each of these breakthroughs built on the ones before, and each one was a surprise. Nobody in 1968 predicted strings would lead to quantum gravity. Nobody in 1984 predicted 5 consistent theories. Nobody in 1995 predicted they'd all be the same theory. Nobody in 1997 predicted that a theory of quantum gravity would turn out to be equivalent to a theory with no gravity at all. The story of string theory is a story of ideas leading to places nobody expected, and that's part of what makes it so fascinating and so frustrating, because the place everyone wants it to lead, a clear prediction that can be tested in a laboratory, hasn't arrived yet. And maybe that's okay. Not every chapter of science ends with a neat experimental confirmation. Sometimes you're in the middle of the story. Sometimes the tools you're building turn out to be useful in ways you never imagined. The way ADS/CFT ended up teaching us about the quark-gluon plasma. The way holographic entanglement entropy ended up connecting quantum gravity to quantum information theory. The way the page curve calculations ended up borrowing techniques from random matrix theory and semi-classical gravity in combinations nobody had tried before. The framework is alive. It's producing new mathematics, new physics, new connections between fields that used to have nothing to say to each other. And there's something else worth remembering. The deepest lesson of string theory might not be about strings at all. It might be about the nature of space-time itself. Before string theory and holography, most physicists assumed space-time was fundamental. It was the stage on which physics played out. Now, a growing number of physicists believe space-time is emergent. It's not the starting point. It's the end product. It arises from something deeper. Quantum entanglement, quantum information, some underlying structure we don't yet have the language to describe fully. The Ryu-Takayanagi formula, the ER equals EPR conjecture, the island formula, the connections to quantum error correction. All of these point in the same direction. Space, distance, geometry, even the smooth fabric of the universe you experience every day. All of it might be woven from quantum entanglement between degrees of freedom that don't themselves live in space at all. That's a staggering idea, and it came from string theory. Not only from string theory, there are other approaches to quantum gravity, loop quantum gravity, and causal set theory and others, and they have their own insights. But the holographic principle and its most concrete realization through string theory have been the primary engine driving this particular revolution in how we think about space-time. So if you're lying there, wondering whether string theory is right, whether it's the final theory of everything, the honest answer is that nobody knows. It might be. It might be a piece of the final theory. It might be a powerful mathematical framework that teaches us true things about quantum gravity without itself being the complete description of nature. Any of those outcomes would be remarkable. Even the last one, even if string theory turns out to be a tool rather than the answer, the things it's taught us would still be among the most profound insights in the history of physics. And you know what? That's enough. That's more than enough. A formula for meson scattering that turned into vibrating strings, that turned into a theory of gravity, that turned into a holographic universe, that turned into the idea that space-time itself is stitched together from quantum entanglement. From Veneziano's beta function to the emergence of space from information in just over 50 years. That's one of the great intellectual journeys of the 20th and 21st centuries, and it's still going. So, let that settle over you. Let the ideas drift. You don't have to hold on to all of it. The Calabi-Yau manifolds, the 10 to the 500 vacua, the page curves and island formulas. Let them blur together like lights seen through fog. What matters is the shape of the story. People trying to understand the deepest structure of reality, making mistakes, following clues, arguing with each other, building something extraordinary, one insight at a time. That's what physics is. That's what all of science is, really. People in rooms, thinking hard, getting it wrong, trying again, and occasionally, just occasionally, catching a glimpse of something true and beautiful hiding underneath the surface of the world. And that's a good thought to fall asleep to. The universe is stranger and more wonderful than it appears. And there are people out there right now, tonight, working on understanding it. They're scribbling equations on whiteboards and staring at laptop screens and arguing over coffee about whether de Sitter space can really be holographic. And maybe one of them will have the next breakthrough. Maybe the next Veneziano or Maldacena is out there right now, about to stumble onto something nobody expected. You don't need to wait up for it. The universe will still be there in the morning, humming along, keeping its secrets for now, patient and vast and quietly, impossibly beautiful. Rest well.